What is the purpose of calculating magnetic declination? Hey, declination of the magnetic. Let's talk about that. Is it to determine the longitude? Is it to determine the latitude? Is it to determine the tilt angle? Or is it to determine the azimuth? So longitude is how far you are east or west. Latitude is how far you are north or south. Latitude determines the sun path, by the way. The tilt angle is how steep you tilt your PV modules. A lot of times it's related to your latitude, not so much your longitude, because you can have a longitude of every different latitude. You can have the same longitude in the tropics as the Arctic, but you can't have the same latitude in the tropics or the Arctic. And then to determine the azimuth, that's got to be the right answer because all those other ones stink. We're going to figure out about this azimuth thing here. Azimuth is what you measure with your compass. Even when you're in AZ for Arizona, where the solar radiation is great, clear air, lots of sun, not many clouds, although it's hot, it is a super awesome place for solar radiation and PV production. We make up for that heat by having great sun. So with the azimuth, we've got north is 0, east is 90, south is 180, west is 270, and the full circle is 360 is also 0 is north. And this system was invented in Babylon by the Sumerians. You know, the 360 divisible by 12, 60 seconds in a minute, kind of works with all those things. It's a different counting system. So here, what we can see is a magnetic compass. We're checking out that sun lining up. And so if you're lost in the woods and you have a magnetic compass, it really helps a lot to know about some of the things that solar professionals at least knew in the past about magnetic declination, about where the sun rises, where the sun sets, different seasons of the year, and how that is a little bit different depending on your latitude and your attitude. Some people might say latitude determines attitude, especially in the winter. So I could remember about hearing about an old timer solar guy that would put a stick in the ground and say, "I'd be back at noon." And that's how he would tell shading. I think he was indigenous. Now we can see this magnetic drift here. The magnetic North Pole is moving faster than it has been. So you can see between 1960 and 1980, it barely moved. And then 1980 and 2000, it moved a whole lot more in those 20 years than the previous 20 years. And then in the next 20 years, it even moved more, a whole lot more. And so then some conspiracy theorists think that this means it's the end of the world. What do you think? And I just think that Russia has a big magnet and they're pulling it over to their side, all those benefits by having the magnetic North Pole where you are. Actually, it's not beneficial because the closer you are to the magnetic North Pole, the worse your compass will work. So take that, Russia. So here's the Earth, and we have the solid inner core of iron. The liquid outer core has some magma, got some crust, even have some atmosphere, very thin relative to the Earth. So we have to be really careful of it. Then that magnetic field, it goes up. It makes these aurora borealis things. It's really cool. It protects the Earth from cosmic radiation. And it tells us how we can orient our solar modules by finding the North Pole with a magnetic compass. It is interesting that we do have these geomagnetic reversals where the North Pole becomes the South Pole. And the last one happened 780,000 years ago. It is interesting too, is that's when humans were evolving super fast. Maybe that has something to do with it. Maybe those magnetic fields weren't protecting our DNA as well. Made some mutations. Some of them were good. Anyway, The time it takes for a complete reversal is 7,000 years. So even though it seems to be moving fast, we're not going to see anything like that in our lifetime or even in our great grandchildren's lifetime. Things are going to be different in 7,000 years. Probably. Wouldn't that be weird if they were the same? Still fighting for that tax credit in 7,000 years. So here we are on the West Coast. And if you're on the West Coast, the magnetic North Pole points to the east. We call that magnetic declination to the east. And we can see that our South Pole of the magnet is pointing towards 200 or 195. Just call it 200. And the real South Pole is 180. So on the West Coast, you subtract to get your true azimuth from magnetic. And on the East Coast, it does the opposite. So you would add. So if it was pointing 20 degrees to the west, we would call that magnetic declination to the west. That would be on the East Coast. The South Pole of the magnetic, that's the magnetic South Pole, would be pointing at 160. And so we would have to add 20 to 160 to get 180. True. Just something interesting. I did get an FAA license, and the numbers on the runway correspond with magnetic azimuth. And so assuming that these compasses are right, this is the magnetic compass. This is a gyroscopic compass that you set to the magnetic compass when you're flying evenly. If you're accelerating, turning and things, it throws it off. And so this one will be more accurate, but then it drifts, as the earth spins, but it looks like they're just about the same. So we've got 3, 4, 5. And so perhaps we are looking at something like 50 degrees azimuth. And so a pilot would call it 050. And so that might be runway 05. And as the magnetic declination shifts, they have to repaint the numbers and rename the numbers on the runway. Isn't that a trip? And if you are getting your drone license from the FAA, I would expect that you probably would have some questions about this kind of thing. And you can use your drone license to do site surveys. So it's all related. In fact, you can just get a single engine airplane pilot's license, and then you can do site surveys with that, flying over places. Neat. Some might call that a tax deduction. So here's a world magnetic declination map. And so you can see these lines, it's telling you the different corrections. And they're putting negative over on the East Coast. So that would be if you wanted to go from true to magnetic. If you wanted to go from magnetic to true, then you would add 10, 20, 30 when you're over this way on these blue lines. And so sometimes pilots want to go from true to magnetic because true is what it says on the map. Magnetic is what it says on the runway, and the way that the tower tells you to fly and all that kind of stuff, or which way to fly your drone. And so you'd take all this into consideration. It is weird that the magnetic North Pole moves midnight to noon. So the Earth is some people say that Gaia is the Earth, is a single organism, and we are just cells in that organism. So there it is for the United States. We can see our magnetic declination map, see where you live, what the magnetic declination is. If you're near the Mississippi River, you don't really have to do any corrections because you're near the zero line. Sometimes these are called isogonic lines. There we have it for 2015. I just want to show you also how relevant this is, knowing magnetic declination. So we have this thing called the Solar Pathfinder, and it does have a magnetic compass in it. So if you're on the West Coast, where they have the counterculture, you can spin this whole base counterclockwise to correct for magnetic declination. And if you're on the East Coast, you would spin it clockwise to correct for magnetic declinations. So we're relevant. This does shading analysis. It's great for site surveys. It doesn't even require electricity. Solar Pathfinder. So magnetic declination helps us figure out our azimuth.